a craft, any object underwater.
We thought we understood the deep, that at 13,000 feet below the ocean there was nothing left to surprise us. But now, an insane new discovery at 5,000 m under the ocean has shocked the entire world.
A groundbreaking discovery in the depths of our oceans may just reshape our understanding of oxygen production.
A silent discovery shattered every assumption, and what began as a small anomaly in a benthic chamber has now become one of the most shocking scientific revelations of our time.
In these are all the metals we need to go and build those batteries.
Does this have the potential to rewrite deep-sea science and history as we know it? Into the abyss. For decades, the scientific consensus held that the deep ocean was a barren desert. Life here was limited to scavengers and microbial communities, saving out an existence in the near-total absence of sunlight. Oxygen, essential for complex life forms, was thought to be nothing more than a scarce commodity in these depths, used up by the few organisms capable of breathing it. Without sunlight, photosynthesis was impossible, and without photosynthesis, oxygen could not be produced. This was the unchallenged understanding of life at extreme depths. But then, in May 2021, a groundbreaking experiment cast this assumption into doubt. A robotic lander, designed to monitor the seafloor, was lowered into the depths of the Clarion-Clipperton Zone, an area over 5,000 meters below the ocean's surface. The lander was equipped with specialized benthic chambers, sealed microcosmic environments intended to track the consumption of oxygen by deep-sea life. What it recorded was nothing short of revolutionary. Inside the chambers, oxygen levels did not drop as expected. Instead, they increased steadily. Over the course of 2 days, the sensors indicated a significant rise in oxygen concentrations, something entirely unheard of in such an environment. There were no flaws in the experiment. The sensors were functioning properly, and the chambers were sealed tightly, preventing any interference from external sources of oxygen. Something in the depths, in the utter darkness, was creating oxygen, and it wasn't alive. This discovery stunned the scientific community, which had long believed that the only way oxygen could be produced in such conditions was through biological processes. But in this case, there was no light, no algae, no photosynthetic organisms to create the oxygen. It was as if, in the deepest part of the ocean, something beyond the realm of biology was working to defy the rules of life itself. The Clarion-Clipperton Enigma. The Clarion-Clipperton Zone is a vast, barren plain that stretches across nearly 4,500 miles of the northeastern Pacific Ocean. It is one of the most inhospitable places on Earth, remote, desolate, and entirely alien to human life. The seafloor here is covered by a fine layer of sediment, dotted with clusters of polymetallic nodules, lumpy rocks packed with valuable metals like cobalt, nickel, manganese, and copper. These nodules have long attracted the interest of deep-sea mining companies, eager to tap into the region's mineral wealth for the global battery supply chain. But beneath this metallic promise lies a far more enigmatic and valuable discovery, one that has the potential to rewrite everything we know about the deep ocean. As researchers continued their experiments in the Clarion-Clipperton Zone, the polymetallic nodules began to reveal an astonishing secret. They seemed to be linked to a phenomenon that no one could explain. Oxygen levels inside the sealed chambers when the nodules were present began to rise significantly, levels that defied all known understanding of the abyssal ecosystem. Some of the chambers recorded oxygen concentrations as high as over 3 times more oxygen than normal in the water. This wasn't an anomaly. Similar results were observed across multiple experimental runs, with various research teams using different methods confirming the same result. The nodules, or perhaps the substances surrounding them, were somehow generating oxygen in complete darkness, deep beneath the ocean's surface. This discovery presented an unprecedented puzzle. How would oxygen be generated at such depths? In the absence of sunlight, without any biological activity? The scientific community was stunned. The most widely accepted theories of deep-sea biology seemed to be wrong. And while researchers began to speculate about potential explanations, one thing was clear. These nodules were more than just valuable raw materials. They held the key to a mystery that could alter our understanding of life in the ocean and possibly the origins of life itself. With the evidence mounting, the question shifted from how to why. Why had no one ever noticed this before? What was it about the nodules that allowed them to produce oxygen in such an extreme and isolated environment? Could this process be a natural phenomenon, previously overlooked? Or was it something far more profound? Something that could change the way we think about energy, life, and the ocean's hidden depths. Anomalies in the abyss. For over a decade, The anomaly observed in the deep-sea benthic chamber experiments was met with skepticism. In each case, the results were the same. Oxygen levels in the sealed chambers steadily increased over a period of 47 hours. Even in experiments where the nodules were removed from the seafloor and placed in sealed containers, without any environmental factors influencing them, the trend continued. Oxygen accumulation, sometimes at rates that surpassed expectations, was observed. The team was baffled. To rule out any biological activity that might be responsible for the oxygen production, they introduced mercury chloride, a potent biocide, to kill off any potential microbial life that might be contributing to the process. However, the oxygen levels still rose. This was perplexing. Not only had biology been ruled out, but other possibilities such as chemical reactions from seawater or gas diffusion were also eliminated. It was then that scientists turned to the possibility of radiolytic oxygen production, the idea that oxygen might be produced through radioactive decay. While this theory was plausible in some environments, it was clear that the phenomenon at play was something entirely new, something that existing deep-sea literature had never anticipated. No known chemical or biological mechanisms explained it. This wasn't a momentary fluctuation. This was a sustained, repeatable event, and the source pointed directly to the black nodules on the ocean floor. Polymetallic nodules had long been an object of fascination for geologists and marine scientists. These dark, irregularly shaped formations accumulate slowly over millions of years, layer by layer, around fragments of organic matter such as shells or tiny bits of debris. The resulting nodules are rich in manganese, nickel, copper, and cobalt. Their surface, marked by intricate dendritic structures, contains oxidized metals, which gives them their dull appearance. But beyond their geological significance, these formations had always been considered inert, unassuming relics of the ocean's past. Nobody suspected that these unremarkable nodules could play a role in something so extraordinary as oxygen production. But when the voltage tests were conducted, the world of oceanography was thrown into turmoil. Franz Geiger, a lead researcher at Northwestern University, spearheaded a series of lab experiments using nodules retrieved from the Clarion-Clipperton Zone. The nodules were immersed in artificial seawater, and platinum electrodes were used to measure any potential electrical output. The team was expecting to find little to no activity, but instead they observed a shockingly high voltage output. Some nodules were generating surface voltages of up to 0.95 volts, nearly enough to power seawater electrolysis, the process of splitting water into hydrogen and oxygen using electrical energy. Even more astonishing was the discovery that when multiple nodules were grouped together, their voltage output increased significantly, as though the nodules were functioning as a network of batteries wired in series. This was an unprecedented finding, with the potential to rewrite science and deep-sea history as we know it. What was once thought to be a simple geological formation now appeared to be generating electrical energy through the interaction of the metals within the nodules. It was a form of natural geobattery, a phenomenon that defied conventional understanding. This realization shifted the course of the research. The electrical energy being generated by these nodules could, in theory, be triggering a chemical reaction within the seawater, resulting in the production of oxygen. And this was a breakthrough. If true, it meant that these seemingly inert formations were far more complex than anyone had ever imagined. They were playing a critical role in deep-sea chemistry, acting as both energy generators and, as the experiment suggested, a potential source of oxygen. The dark oxygen phenomenon. For decades, scientists believed that oxygen on Earth came from two primary sources: photosynthesis, driven by sunlight, and in rarer cases, radiolysis, the splitting of water molecules through radiation. This was the foundation upon which we built our understanding of life and the planet's atmospheric conditions. However, deep beneath the ocean at the crushing depths, where light is a forgotten concept and life clings to the slimmest slivers of possibility, an entirely unexpected discovery would turn this established knowledge on its head. It was a phenomenon that would come to be known as dark oxygen production, a process by which oxygen was formed, not through sunlight or biological activity, but through an entirely inorganic mechanism. At the heart of this strange new reality are the polymetallic nodules, mysterious fist-sized rocks that lie scattered across the ocean floor. These unassuming formations were long considered nothing more than geological curiosities, but they hold a secret far beyond their outward appearance. These nodules, laden with metals like manganese, nickel, and copper, possess an inherent electrical potential capable of triggering reactions that can produce oxygen. Under the intense pressure and sub-zero temperatures of the deep sea, they become more than mere rocks. They become powerful electrochemical machines. In a series of groundbreaking experiments, researchers discovered that these nodules create voltage gradients strong enough to trigger the oxygen evolution reaction, a process that splits water molecules into hydrogen and oxygen. What's astonishing is that this reaction occurs naturally, driven by the nodules themselves, without the need for external energy input. As the oxygen bubbles slowly formed and began to accumulate, it became clear the seafloor was not just a lifeless abyss, it was, in a way, breathing. Lab simulations confirmed the discovery. Manganese oxide, a key component of the nodules, had been found to act as a highly effective catalyst for this reaction when combined with nickel and copper. In the cold, pressurized depths of the ocean, these minerals could initiate the release of oxygen, far beyond what could be attributed to contamination or external influences. In controlled experiments, oxygen production rate is about 400 milligrams of oxygen per square meter every second. This was no random fluctuation. This was a consistent, measurable phenomenon that far surpassed any atmospheric or biological interference. Perhaps the most shocking aspect of this discovery was that the oxygen was not simply diffusing from the surface or from any external sources. It was being generated on the seafloor itself, at the very site of the nodules. This was not the simple result of biological decay or external contamination. It was the creation of a critical element from the Earth's depths, driven by the inorganic properties of the minerals buried deep below the ocean's surface. When the seafloor breathes, the implications of the dark oxygen production phenomenon are profound and far-reaching. Until now, Earth's oxygen production has been exclusively linked to photosynthetic processes in light-rich environments or, on rare occasions, radiolysis, from radioactive decay, deep within the Earth. But the discovery of DOP forces a dramatic shift in our understanding of both the planet's oxygen cycle and the very conditions necessary for life to thrive. For one, this discovery opens the door to a potential explanation for how life survives in the deep ocean, where sunlight cannot reach and oxygen levels are notoriously low. Researchers have long puzzled over how deep-sea ecosystems, many of which depend on oxygen, could possibly sustain themselves without the benefits of sunlight-driven photosynthesis. The existence of DOP, however, provides a possible solution. Polymetallic nodules could be fueling these oxygen-starved ecosystems, allowing life to persist far beneath the surface. Entire communities of organisms, including bacteria, fish, and other deep-sea creatures, may owe their very existence to these seemingly unremarkable nodules, which may be quietly generating the oxygen they need to survive. The discovery also opens up new questions about the origins of life on Earth. If oxygen can be created through electrochemical reactions in complete darkness, it suggests that aerobic life forms could have evolved not in shallow, sunlit seas, as is commonly believed, but in the deep, dark trenches of the ocean, where light never penetrates. This challenges traditional theories about the development of life and points to a far more complex and perhaps older mechanism for life's emergence. As scientists begin to fully grasp the implications of this discovery, the question shifts from whether the seafloor breathes to how long we've misunderstood the deep ocean's role in the oxygen cycle. The realization that oxygen can form in total darkness without any biological intervention rewrites the very foundations of how we think about life on Earth and the environments that sustain it. For decades, we looked at the oceans as a vast, silent realm, devoid of life-giving properties. But now we understand that the deep sea is a far more active and complex environment than we ever imagined. A place where oxygen is born, quietly and persistently from the very bedrock of the Earth itself. The implications of this discovery will continue to unfold in the years to come, potentially changing our understanding of both the planet's ecosystems and the origins of life itself. History itself might be rewritten. The seafloor, it turns out, is not as silent as we thought. It's breathing, and it's far more alive than we ever realized. Rewriting the oxygen story. For centuries, humanity believed we understood the origins of Earth's oxygen. The prevailing theory, deeply rooted in the scientific community, stated that photosynthetic organisms like algae and cyanobacteria were the first to generate oxygen. Sunlight provided the energy necessary to convert carbon dioxide and water into glucose and oxygen. This process, known as photosynthesis, was thought to be the starting point of Earth's oxygenation. But this narrative was built on a foundation that is now beginning to crack. The discovery of oxygen production at the seafloor, catalyzed by the polymetallic nodules, introduces a radical new understanding of Earth's early biosphere. If oxygen can be produced in the complete absence of light, then the origins of life and oxygen itself may have been vastly different from what was previously thought. The implications of this shift are profound. If these nodules, those unassuming potato-sized rocks, were capable of generating oxygen without sunlight, it raises the possibility that life on Earth may have originated in the darkness of the ocean floor, long before the rise of photosynthetic organisms. Instead of life beginning on the surface, where light could penetrate, perhaps it began in the depths, powered by the electrical gradients and mineral catalysts found in the seafloor. This revelation changes the entire timeline of Earth's evolution. If oxygen could emerge from these chemical processes deep beneath the ocean, then photosynthesis might not have been the initial spark of life at all. This rewrites history, offering a completely new perspective on the origins of life on Earth. The deep-sea ecosystem, often overlooked in the study of life's history, could hold the key to understanding not only how Earth became oxygen-rich, but how life itself may have begun. This revelation is not merely a scientific curiosity. It has the potential to reshape how we think about life on Earth, its origins, and the mechanisms that sustain it. The implications could stretch far beyond the oceans, offering new insights into the development of life in other extreme environments on Earth, and potentially even on other planets. This isn't just a minor scientific adjustment, it's a total reevaluation of Earth's biological history. It suggests that life could have started in the deep ocean, powered by the minerals beneath the seafloor, long before the sunlit surface became the cradle for photosynthetic life. This is a seismic shift in our understanding of biology, and it could redefine the parameters by which we search for life beyond our planet. The mining of these polymetallic nodules, with its potential to destroy not just a resource but a key piece of the Earth's oxygen cycle, could irreversibly alter the course of our understanding of life itself. If we destroy these crucial elements of the ocean's life cycle, we may erase not just an ecological system, but a critical part of Earth's historical narrative. Beyond Earth. This insane new discovery at 5,000 m under the ocean shocked the entire world, but its implications stretch far beyond our planet. The idea that oxygen can be generated in an environment devoid of sunlight opens up entirely new avenues for the search for extraterrestrial life. Moons like Europa and Enceladus, both enveloped in thick layers of ice and harboring vast subsurface oceans, have long been regarded as promising candidates for the existence of life. However, scientists had always believed that the key ingredient for life, oxygen, could only be sustained in environments where sunlight reaches, sparking photosynthesis. But the discovery of dark oxygen challenges that belief. In the frigid depths of Earth's oceans, where no sunlight penetrates, a chemical process has been quietly at work, producing oxygen without the need for light. This process, driven by metallic interactions between minerals and water, suggests that similar conditions could exist elsewhere in the universe. The oceans of Europa, Enceladus, and other distant moons once thought to be inhospitable to life now offer a fresh perspective. If such chemical reactions can occur in the cold, dark waters of alien worlds, it is entirely possible that life, powered by chemistry rather than sunlight, could thrive beneath their icy surfaces. In essence, the search for life beyond Earth may no longer be confined to the Goldilocks zone, the habitable zone around stars where conditions are right for liquid water and photosynthesis. Instead, it may extend to the frozen moons of our solar system and perhaps beyond, to exoplanets orbiting distant stars. The concept of dark life, organisms thriving in the absence of sunlight, is no longer a fantasy. It is a scientific reality, and it could be the key to unlocking the mysteries of life beyond our world. The discovery of dark oxygen doesn't just expand the scope of where we might find life, it transforms our understanding of what life can be. These new revelations challenge the very definition of life itself, suggesting that it might not require light at all. This opens up a whole new realm of possibilities for astrobiology, one that could radically shift the way we look at the universe. If life can survive in the extreme, lightless depths of distant moons, it could be everywhere, hidden in the shadows of icy seas or beneath the surface of seemingly barren worlds. What lies ahead? As we process the magnitude of this discovery, we must confront the responsibility that now accompanies it. The revelation of dark oxygen production has brought with it an urgent need for reflection on how we treat our planet's deep-sea ecosystems and how we understand life itself. The global race to mine the deep sea for its riches has already begun, with corporations eager to extract the polymetallic nodules that are believed to hold vast amounts of rare minerals, essential for powering our modern world. The technologies being developed to harvest these resources are advancing quickly, but with little regard for the potential environmental consequences. The discovery that the very nodules targeted for extraction may be responsible for generating oxygen in the deep sea sends a chilling message. Destroying them could have unforeseen consequences, not just for marine life, but for the broader functioning of Earth's biosphere. If the oxygen production from these nodules is disrupted, it could lead to the collapse of deep-sea ecosystems that depend on this unique source of oxygen, systems that are vital to the overall health of our planet. This is no longer a simple matter of preserving biodiversity in the depths of the ocean. It is about the preservation of planetary function. By mining these nodules, we risk disrupting a crucial process that has been quietly sustaining life at the deepest levels of the ocean for millions of years. The potential consequences are staggering, not just for the creatures of the deep, but for all life on Earth. As we move forward, we must ask ourselves, what kind of world do we want to leave behind? One that has destroyed the very systems that support life in the name of progress, or one that preserves the delicate balance of nature, recognizing the deep interconnected threads that tie every part of our planet together. The seafloor is not just a repository of minerals. It is a living, breathing part of our planet. It is active. It is alive. And it holds secrets older than light itself. The discovery of dark oxygen production is not just a scientific breakthrough. It is a profound wake-up call. We stand at the edge of a new era, where the choices we make now will shape the future of our planet and our understanding of life itself. As we look to the stars, we must also look within, towards the depths of our oceans, where the secrets of life on Earth and beyond are being uncovered. If oxygen can form in the dark, could life begin without light? Share your thoughts in the comments. Thank you for watching this video with us, and catch you in the next one.